Algebra 2, Concept 28. Solve exponential and logarithmic equations. So let's start with some vocabulary definitions and formulas. In this section we're going to be solving exponential and log equations. We'll use two different methods. The first method uses what we call the property of equality for exponential and log equations. So if bases are the same, then you can set the exponents or the log values, depending on what kind of equation you're working with, equal to each other and then solve. The second method we'll use is to use the inverse form of the function to solve either exponential or log equations. So to solve them, if you're unable to have the bases be the same, then you can simply switch forms. So if you have an exponential equation, you can switch it to log form and solve. Or if you have a logarithmic equation, you can switch it to exponential and solve. Lastly, we'll use the log properties that we learned in the last concept just to help us solve equations. So real quick, here's a review. Remember, the product property allows us to rewrite the logarithm as a sum. The quotient property allows us to rewrite the logarithm as a difference. And the power property allows us to rewrite the logarithm with the power being multiplied by the log. And remember, we can use these properties to expand, or we can use the properties to condensed. Alright, so let's start by solving an exponential equation using method 1. So we're going to find a common base that can be raised to different powers to equal the bases in the original problem. Then we're going to set the powers equal to each other, because that's what the property of equality allows us to do. And then we can solve for x. So number 1, we have 100 raised to the x power equals 1/10 raised to the x minus 3. So we look at our bases and we think, is there a number that I can use as a common base raised to different powers to rewrite 100 and a 10th? So I think about 10. I can square 10 to get 100. And then I'll put that in a parentheses because that represents my current base, but it's still raised to the x power. And then 1/10 I can raise to the negative 1 power. Or sorry, I can take 10 and raise it to the negative 1 power to equal a 10th. I put that in a parentheses because that is still raised to the x minus 3 power. When you raise a power to a power, remember you multiply. So we'll go ahead and do that. Now that property of equality says that if you have the same bases raised to different powers equal to each other, since the bases are the same, then that means the powers have to equal each other. So we just use that logical thought and we set those exponents equal to each other. And then we'll solve. And in this case we end up with just a simple equation. So x equals 1. And our next problem, we've got 9 to the 2x power equals 27 to the x minus 1. So think about 9 and 27 and a common base that you could raise to different powers to equal those numbers. So I think of 3. 3 squared is 9, but I still need to raise that to the 2x power. 3 to the third power is 27, but I still need to raise that to the x minus 1 power. When you raise a power to a power, you multiply. So let's multiply those powers. And now, since our bases are the same, we can set those exponents equal to each other. Then we solve. So x equals negative 3. Alright, now let's use the property of equality and solve some logarithmic equations. So if you look at the box on the right, you'll see the steps there to solve log equations. So look and see if the log bases are the same. And if you have 1 log equal to the other, or if you can rearrange the equation so that it reads like that. If you can, then you can set the values of the logs equal to each other and simply solve for x. So on number 3, we have log base 5 of 4x minus 7 equals log base 5 of x plus 5. Since our log bases are the same and I have one log set equal to another, I can simply set the values equal to each other and then just solve that simple equation. So we get 3x equals 12 or x equals 4. We want to check these answers, so we just plug it back in. We've got log base 4 of 16 minus, log base 5 of 16 minus 7, which is 9. Log base 5 of 4 plus 5, which is 9. So that checks for us. Number 4, we have the natural log of 2x minus 4 equals the natural log of x plus 6. Remember, the ln, or the natural log, is base e, so we can set those values equal to each other and solve. So x will equal positive 10. And then just a quick check. So we have the natural log of 20 minus 4, which is 16, equals the natural log of 10 plus 6, which is 16. So that checks. Now sometimes you'll be unable to rewrite your bases as the same base, different powers, when you're dealing with exponentials. So in that case, we'll use method 2, which is to change forms. So if it's exponential, you can rewrite in log form. So with our first example, we'll have log base 4 raised to the x power equals 11. So you can evaluate log base 4 of 11 on your calculator. Remember that you can use change of base, so the log of the value, or 11 divided by the log of the base, or the log of 4. And if we round to 3 decimal places, we'll get 1.730. You can always check that by taking the base 4 and raising it to that power, and you'll get very close to 11. Alright, our next example, 7 and 15 are our bases. There's not a number that we can raise to different powers that'll give us 7 and 15, so we can switch forms then. So we can rewrite it as log base 7 raised to the 9x power equals 15. So we'll divide by 9 to solve for x. So on your calculator, you can do change of base, the log of 15, divided by the log of 7, and then once you get that value, you can divide it by 9. If we round to 3 decimal places again, that'll be approximately 0.155. Alright, now let's switch to log equations. So we don't have one log set equal to each other, so we can't use the property of equality. So in this case, we can switch forms. This time we'll rewrite it in exponential form. So 4 to the 3rd power equals 5x minus 1. So solve for x. 5x equals 65. So x equals 13. Same thing for our next example. Log base 2 of x minus 6 equals 5. So switch forms. 2 raised to the 5th power equals x minus 6. So we'll add 6 to both sides. X equals 38. Let's check that. So if we plug in 38 minus 6 is 32, and we're seeing if log base 2 of 32 equals 5, and it does, because if you raise 2 to the 5th power, you'll get 32. And then let's check the one before. I think I forgot to do that. So log base 4, 13 times 5 is 65, minus 1 is 64. So we're looking to see if 4 to the third power equals 64, and it does. Sometimes when you're solving log equations, you can use the properties to help you. So if you look at example A, you'll see that you have one log expression plus another, and it is the same base, base 2, equaling 3. So we can condense that.
Okay, I'm done and I'll be back on door duty.
Right. So since those logarithms are added, we can use the product property to put them together as a product. So we can rewrite it as log base 2 of x times x minus 2 equals 3. Now let's rewrite that in exponential form. So 2 to the third power, which is 8, equals, and then I'm going to go ahead and distribute that x. So that'll give me x squared minus 2x. Now I'll subtract my 8 over, so x squared minus 2x minus 8, and then see if it factors. So two numbers that I'll multiply to give me negative 8 and combine to give me negative 2, which is negative 4 and positive 2. Set them both equal to 0, so x equals positive 4 and x equals negative 2. We need to check these. So we put them back into the original. I get log base 2 of 4 plus log base 2 of 2 equals 3. And that does check. When I place negative 2 in, I cannot have a log that is negative because there's no power that I can raise my base of 2 to that'll give me a negative number. Alright, now let's look at B. So the first thing I notice is I've got 4 multiplied out front, so I can rewrite that as the natural log of negative x to the 4th power equals 18. Then I can rewrite it in exponential form. Another way I could do that, however, is that I could subtract my 3 over, and then I can divide by 4. So I get the natural log of negative x equals 4.5. Now I can rewrite that in exponential form. So e to the 4.5 power equals negative x. I just divide by negative 1. So x equals, and is approximately equal to negative 90. Now in example C, I can combine that as a product. So I'll have log base 3 of x minus 9 times x minus 3 equals 2. So if I rewrite in exponential form, 3 to the 2nd power equals x minus 9 times x minus 3. Now we just have to follow the math. So we're going to square that and get x squared minus 12x plus 27, and then subtract my 9, so x squared minus 12x plus 18, and see if it factors. So two numbers that will multiply to give me 18 and combine to give me negative 12. Well, there are none of those, so I can pick out A, B, and C and use the quadratic formula. So x will equal negative 1, or I'm sorry, positive 12, plus or minus the square root of negative 12 squared, which is 144, minus 4 times 1 times 18, all divided by 2 times 1. So simplified, I'll get 12 plus or minus the square root of 72 over 2. I need to keep simplifying, so 12 plus or minus, now 72 is the same as 36 times 2, so I can pull out the square root of 6 divided by 2. I can divide everything by 2, so I'll get 6 plus 3 times the square root of 2, and 6 minus 3 times the square root of 2. When I put that back into my equation to check, 6 minus 3 times the square root of 2 does not work. And you can check that just on your calculator. Alright, now let's talk about some real-life problems. So as a town gets smaller, the population of its high school decreases by 6% each year. The senior class has 320 students now. In how many years will it have 100 students? Write an equation. So we've got a situation of exponential decay. So you can remember that that formula is our ending amount equals our starting amount times 1 minus the rate raised to our time. So our ending amount is 100, starting is 320, 1 minus 0.06, because we'll change 6% to a decimal, raised to the t power. Start by dividing 100 by 320. So you get 0.3125, which equals 1 minus 0.06. Oh, and let's go ahead and do that. So that would be 0.94 raised to the t power. Now we have an exponential equation to solve. So let's put it in log form. So log base 0.94, and the value is 0.3125 equals the time. So get your calculator and do the change of base, and you'll see that the time is about 18.8 years. Second real-life problem is the sound intensity problem. Again, like we did earlier. It says on A, the noise level inside a convertible driving along the freeway with its top up is 80. With the top down, the noise level is greater, it's 93. Find the intensity. So we'll put in what we know. So we know with the top up, the intensity is, the sound level is 80. And then our formula is I divided by that initial intensity, which we're told is 10 to the negative 12. So you can divide both sides by 10 and get 8 equals log of I over 10 to the negative 12. And then we can rewrite in exponential form. So remember this is log base 10. So 10 to the 8th power equals I over 10 to the negative 12 power. Multiply both sides by 10 to the negative 12. So I, or the intensity, equals 0.0001 watts per meter squared. Now let's look at with the top down. So with the top down, our sound level is 93, and then we'll set that equal to our formula, plugging in 10 to the negative 12. So we'll go through the same steps. Divide both sides by 10, so we'll have 9.3 equals log of I over 10 to the negative 12, and then we'll change to exponential form. So that's 10 to the 9.3 power equals I over 10 to the negative 12. Multiply both sides by 10 to the negative 12, and you'll get the intensity equals 0.0020 watts per meter squared. Excuse me. So you can see the intensity is a little greater. Now do the independent practice problems, pause the video, and then come back and check your work. So for problems 1 and 2, we can, on 1, rewrite as the same base and set the exponents equal to each other, and you'll get -5/3. On number 2, we can set the log values equal to each other, solve, and you'll get x equals 3. For number 3, you can switch forms and then use your change of base divided by 6 so that you'll get approximately 0.253 rounded to thousandths place. Number 4, you can switch forms and you'll get x equals 123. On 5, use the property to condense that log and then switch forms so you'll get x equals positive or -1. You need to check both of them and they actually both work. All right, and that concludes the notes for concept 28.